Professor Luca Ferranini from Politecnicum di Milano. Luca will speak about predictive control oriented models of a domestic air-to-water heat pump under variable conditions. Luca.
Yes,
thank
you. Thank you very much, Moshe. Thank you for inviting me to this workshop. Can you see the slides correctly?
Yes, it's okay, and we can hear you quite good. Yeah.
Very good, very good. So thank you very much. This is the title of the presentation. Actually, at the end, I will also talk a little bit of tertiary use, not only domestic heat pumps. So basically what I'm talking about is control problems, in particular control of the temperature in buildings where we are using heat pumps to generate heat and radiant panels or radiators or even fan coils to distribute heat inside the building. So the general idea, so we don't need to tell so much, is reduce energy consumption while preserving comfort. And the more specific goal of this activity is to try to understand to which extent we are able to do this goal, to reach this goal through control techniques. So we are not studying any other technologies. We are just trying to push control techniques. And in particular, we do not use generic control algorithms, but real-time optimal control over a finite horizon that we call the model predictive control. So the general challenge is basically how to perform an optimal control. So how to solve an optimization problem, of course, in real time, when the model under investigation, under control is not perfectly known. So if everything is known mathematically, then we can do marvelous things. But in general, this is not the case. So basically, the challenge which is behind this work and the similar kind of works is how well we need to understand the system under control in order to control it in a sufficiently good way. This is not my concept. This is a very well concept. And the last time I heard about this was during the Afeka conference, during the plenary talk by Benjamin Recht, which is a professor from California, from Berkeley, California. Okay, so the practical problem, the practical target is to provide an estimation and prediction of the behavior of the heat pump, which is a device which is very well known, very well studied, but still not very, let me say, their model are not very used in practice. And we studied this in order to be able to decouple the generation from the delivery of buildings, of energy to the building. So this is basically, so when you need a little bit of energy in your building, you may not use the heat pump because it's not convenient. So you needed to put an energy storage device, as we have seen before, just to decouple the generation from the usage, from the delivery. There are moments where the heat pump is more efficient. It's better to use it there than store the energy and use it later. That's the main simple idea. And model predictive control does exactly this job. Makes a prediction for the future based on the model, and then trying to optimize the behavior of the system. So this is the testing facility that we used. It is actually a laboratory located in Denmark, in DTU, where there is a heat pump with a tank, and it is associated with the distribution system, which is able to serve a load which is made by two houses, one with one floor, another one with 3 floors. There is, of course, a mixing valve, three-way mixing valve, in order to regulate the mass flows inside the house, inside the load. Again, in order to decouple even more the generation from the usage. So the tank is able to decouple, is the energy storage element, but also the three-way valve is able to enforce a recirculation of water. So again, to reduce the temperature inside the pipelines. So the most difficult task, sorry, I come back. So the idea is how to regulate, how to control the heat pump, how to say to the heat pump, you have to work now or later to produce water at a given temperature in order to serve the load when there is somebody in the house, when somebody is providing their own desires about the profile of temperature. So we studied a little bit the main components. In this case, in this presentation, I do not talk about the model of the house, which is assumed to be fairly simple, which is usually the case for mid-term control, mid-term horizon control. So we studied the tank, the water tank, and the heat pump. So basically, we used a vertical stratified model for the heat for the hot water tank, and we compare it with 24th order system in order to understand which is basically the root mean square error. And we see, of course, that based on the number of layers, the number of nodes that you put inside this model, you have a different quality of results. And for the heat pump, that's one practical problem, because when you buy the heat pump, you know that there is a local controller inside which is able to switch on and off the local pump, which circulates the water inside the condenser side. And there are other switches and other controllers inside that are not very well documented. So what we did is to develop a reference model thanks to some library, thermolib library, in order to model correctly the gases inside and all the phenomena. In the end, we collected the data from the tank, from the various level of the tank. We measured the electrical power, and then we managed to experimentally validate the reference model in all the ranges that we are interested in. For the heat pump control, we need a model. Usually, where sampling times are in the order of minutes, in this case, we are using 15 minutes, the COP can be assumed as a nonlinear algebraic function. And there are usually a lot of combination of possibilities to approximate the behavior of the COP. In the past, we studied linear and quadratic functions with 1 to 3 different inputs. Typical inputs are the open air, so the external temperature of the water that you have to heat, and the power itself, or the compression factor. So the main problem, so one of the problem actually in the modeling of this system, so trying to reach the goal that we said at the beginning. So what is the simplest model to achieve an optimal control is not to model the mass flows between the condenser side of the heat pump into the tank, because that's, let me say, the most straightforward way, because we have no measurement of the mass flows. So how much water is coming into the tank and is recirculating in the tank. So what we did is to model the heat as a function of, simply as a function through the COP of the electrical power, and then we distribute it in the tank as an exogenous input. So as an input of the model. And what we did is to try to understand how we have to distribute this heat between the layers and how many layers we should use with such a simple model of the system. As you can see here, there are errors in this simplification. And let me say, a good approximation is with a model of 4 layers with heat as an input and not mass flows as input, okay? And that's the typical errors that we obtain. So approximately a couple of degrees on the temperature inside the tank, which is an acceptable error. The temperatures are in the range of 40 degrees, more or less. So we set up a control problem, an optimal control problem. So we have our reference model, our detailed model of the system. And then we set up our controller. The controller is based on an estimator, a Kalman filter-based estimator. And then we have a control-oriented model, which is a simplified model of the whole system. So the reference model has actually the mass flows and the temperatures and the stratification of temperature and the heat inside the tank, all of that, while the control-oriented model has a simple tank model and a simple COP model. So that's the challenge. If our model inside the controller is fair enough to control the system and simple enough to be implemented in real time. So here there is the discussion, the description of the cost function, which is basically a combination of cost, which means electricity cost, and comfort, which is a tracking error with respect to the set point. There are some constraints on the temperatures of the zones inside the building, on the water to be used inside the radiators, and so on. So we set up in the end a nonlinear model predictive control because the system is nonlinear due to the COP and the thermo-hydraulic dynamic of the system. And then we used some, let me say, classic technique to discretize the system through a Runge-Kutta algorithm, classic Runge-Kutta algorithm with integrating shooting integral of 4. And then we solved a discrete optimization problem with a prediction horizon up to 12 hours, from 6 to 12 hours. Nothing changes. We compared what we did with this optimal control problem with the classic heating curve control, which basically it's a table, it's a function, which tells you which is the right temperature for the tank based on the external temperature, more or less. Okay, so if outside it's very cold, then you need to increase the temperature in the tank. That's it. We took this exactly from the same manufacturer of the heat pump, because this is actually what is implemented in the local controller of the heat pump. We simulated one typical day in winter where the external temperature is around 0 degrees. And then we have seen that the comfort bounds are basically easily, let me say, matched by any kind of controller. So from the optimal control down to the heating curve element, we are able to track the temperature basically inside the building. But the electrical power that we use is a bit different. Okay, so we see in the dashed line the price that we invented, the real-time pricing that we are inventing. And we see that our technique, of course, is trying to use less energy when it costs a little bit more, and vice versa. When it's a little bit cheaper, then you can use it a little bit more electrical energy. So in the end, what you obtain is that your heat pump is able to work at a lower temperature. And since the efficiency of the heat pump depends on the temperature of the water that you have to heat, you can gain a lot in terms of efficiency. Of course, so when the heat pump coefficient of performance is high, maybe you are not using that much. It's the heat pump, so the overall saving is less if you look at the money that you spend or electrical energy that you spend with respect to the COP increase. So basically, what we proved is that it's totally feasible to set up an optimization problem in real time, even with non-linear models. Our algorithms run in MATLAB on a standard PC, and they usually take less than 1 minute to run. So we are talking about a non-linear optimization problem with 20 points in the future with inside the horizon. And in the end, we are able to save a significant amount of electrical energy with respect to more traditional controllers. What we are doing at the moment, so we were encouraged by the results. So we tried to move from residential, as I said, to tertiary field. In this case, we took a building of Politecnico, which is a building with 4 stories, 18 spaces, 14 classrooms inside. And the HVAC is a classic industrial one. So you have air handling units, two of them serving 2 floors each. We have 2 heat pumps, one air to water and one water to water. There is a well in the garden to do so. And then there is a complicated system of distribution of the water through radiators and fan coil. And also the air handling unit contains also some temperature control for the water. So basically what we did is to simplify the model. As usual, what we are doing actually is to simplify the model to the most essential parts for the thermohydraulic system. For the building, we try to identify the main responses through the classic gray box model. So the heat transfer coefficient were assumed to be unknown, and you identify them from the data. We put a lot of sensor inside the Smart City project that Athanasius mentioned before. And so we were able to capture the main dynamics of the room temperature and the wall temperatures. In the end, we are setting up a nonlinear MPC. So the only difference is mainly the scale. Now the scale is much, much bigger than what we have seen before. And there are a little bit more devices and more industrial ones. So air handling unit, different COP, and so on. We are also trying to use neural networks, not only differential equations to model our system. And we are getting some, let me say, good results. Let me say, I think they are less good results because the quality of the tracking is a little bit worse, but the advantage is that you just take the data and magically you are able to set up a controller. So we use the neural network. We train a neural network based on the data, and then we transform the neural network model into a nonlinear model that we use into the nonlinear MPC. This is a quite innovative way to deal with this, but it's a combination of a neural network and the MPC approach. We are going to deal in the future with a more reinforcement learning, machine learning approach, even if personally I'm not so positive towards this approach, because so we just took some bites of this problem, but we immediately understood that it's less easy. For sure, it's less easy. For example, the training of control agents is more complicated. You need a huge amount of data. Even in the first talk, Athanasius mentioned this. So 1 year data is not enough. Usually for a heat pump, you need maybe a few minutes of data, and for a room, maybe you need a few days of data, but the machine learning needs a huge amount of months of data. And this is exactly what we are experiencing even in simulation. And if you make a mistake, if you are not if you happen not to use sufficiently rich data, you have an unstable behavior. So for some days, this is just a set point moving from 17 degrees to 22 degrees. You see the first days, your system is tracking very well at the set point. And after a while, something happens, something goes wrong, and you are not able to track it very well. This does not happen if you're using even a standard PID control. This means that we still have to work a lot on this subject. And also another point that is, again, disappointing me, if you zoom a little bit when you think that the system is working correctly, you see that you are not even able to track very well the temperature. So nothing important, let me say, we are talking about 0.1, 0.2 degrees. But if you zoom a PID control performance, you see the temperature perfectly tracked. So it means that we are going to study this. My expectations are not so high, let me say, but maybe a combination of model-driven, so it means equation-based controller with more data-driven, which basically means you try to fill your ignorance on the model thanks to lots of data. Maybe a suitable combination of these two approaches may have a better performance in some cases. We are looking for, let me say, these positive cases. At the moment, we are still working on that. Okay, that's all from my side.
Thank you, Luca. It's very, very, very interesting, especially that. I mean, you also have some mechanical engineering people. I mean, people that are more familiar with the thermodynamics of the system and the control. Your colleagues.
I see some question on the chat. So there is one on air water heat pumps. Yes, for sure they have some limits. The one that we know that were told us by the manufacturer, we implemented them. And for the Denmark case, there is also an additional device heating the external part of the system just to inhibit the formation of icing on the external fans. We didn't model them explicitly because basically this is for us an additional electrical consumption, which is able to protect the heat pump. And that's it. And for our case, the last that we have seen, again, we didn't model it because one is water to water, and that's fairly simple because the temperature of the water is more or less constant for us. And the other one is really protected in a special building, so we never reach better temperatures, let me say.
Do you think, Luca, can you hear me?
Yes, very well.
Did you try to do it also during the summertime, meaning for hotter days? Then you will use it on the reverse cycle for cooling the building.
Yes, I understand that. No, we just made some experiments, but some simulations, sorry. But we didn't investigate that much. Let me say the COP formulas should be different, of course, but the rest of the simulation model should be the same because the thermodynamic properties of the walls and pipelines are the same. So we made just a few simulation, and that's it. So we didn't experience any big problems. Let me say, we didn't model.
It would be interesting. I mean, we could use it in one of our buildings. That would be very interesting to do it.
Yes.
Maybe we should, yeah.
Could be nice. It could be nice. You have more problem of cooling than heating,
yes.
probably.
You have to understand that yesterday we had 40 degrees outside, so it would be.
we have still the heating on in Milan. So actually not in Milan, but in the north of Italy. So our heating system is still working these days. So dramatically cold.
Okay, I think that we are over. There's another question from Ellie. Do air water heat pump have a limit of the output? Yeah, we were talking about COP in water. The water seems to be higher.
Yes, this is exactly what we had. So we had the data sheet of the two heat pumps, and this one is tremendously more performant than the other one in the conditions where we simulated, which is basically in a winter day. So where air to water usually is not working very well, while water to water is a little bit more performing. Actually, this opens the way to another problem, because I don't know why they installed two heat pumps, so I can imagine, but so it opens the way to how to modulate somehow, if it is convenient, the power needed between the two heat pumps. But we did not investigate it yet, this problem. So we just use them as a unique machine which is able to deliver heat, even if we model them separately.
Okay, I want to thank